Alright, so in this video I'm going to be going through the January 2010 Unit 1 paper on the particle physics and electricity. So let's start off with some particle physics. So we've got hadrons are a group of particles composed of quarks. Hadrons can either be baryons or mesons. What property defines a hadron? And so a hadron's any particle that experiences the strong force. That's the key thing that features a hadron, because the opposite leptons can't experience the strong force. So experiences the strong force. Okay. And what is the quark structure of a baryon? So baryons have 3 quarks or antiquarks. That's what makes them different to a meson, which has a quark and an antiquark. So it has 3 quarks, and an antibaryon has 3 antiquarks. Okay, what's the quark structure of a meson? So this one is made up of a quark, as I said before, and that looks like a divide, and antiquark. So that's some of your basic definitions right there. Easy. So state one similarity and one difference between a particle and its antiparticle. So the difference between a particle and its antiparticle is charge. So an antiparticle has the opposite charge of its particle. You could also argue that it has things like the opposite baryon number, opposite lepton number, but that would depend what kind of particle it is. But it's always opposite charge, even neutral. And then what we can go for, so in terms of things that are the same, would be its mass is the same, its rest energy therefore would be the same. So that would give you some basic similarities and differences. Okay, so I'm going to complete the table below, which lists the properties of an antiproton. So an antiproton has a charge of minus 1.6 times 10 to the minus 19 coulombs, because a proton is +1. It has a baryon number of -1 because it's an antiparticle, and its quark structure is exactly the opposite of a proton. So a proton is up, up, down. That means an antiproton is anti-up, anti-up, anti-down. So that completes that fairly basic question straight away. Alrighty, so to round off question 1, we're going to look at an interaction here. So you've got a K- meson, strangeness -1, and it decays in the following way. State with a reason what interaction is responsible for this decay. So if we have a look, we know that the particles, if we look in terms of strangeness, this one's got -1, this one's got 0, and that's got 0. So if strangeness isn't conserved, that means it's going to be caused by the weak interaction. Because if it was strong, we would know strangeness would be conserved. So it's going to be the weak interaction. And we know that because strangeness is not conserved here, because it goes from -1 to 0 on the far side. And we know if strangeness is not conserved, it's not the strong, it must be the weak interaction that's caused this decay. Those are the type of interactions that cause decay. Okay, so then final part of this question 1, state 2 properties other than energy and momentum that are conserved in this decay. Well, if it's a legitimate decay, all the usual things must be conserved. So for instance, charge must be conserved, lepton number has to be conserved. We could have gone with baryon number. Kind of scribbled over my R there, but we've got baryon number there. It's specifically in terms of lepton number, it's actually muon lepton number is conserved, and those are the things that have to be charged conserved in any reaction, so you could go with pretty much anything there. Okay, so that concludes question 1. So we've got a fluorescent tube filled with mercury vapor at a low pressure. So we're looking at fluorescent bulbs essentially. In order to emit electromagnetic radiation, the mercury atoms must first be excited. What is meant by an excited atom? So an excited atom is an atom with an orbital electron and where is that orbital electron? It's at an energy level above ground state. So it could be any of the energy levels, it's just not at ground state. Those would all be excited state. Above ground state. Okay. So that's what is excited. Obviously ionized would be when it completely leaves the atom, but excited is while it's within the atom. Okay, so describe the process by which mercury atoms become excited in a fluorescent tube. So we've got briefly in the process what we've got a filament that's emitting electrons. They collide with mercury and cause the mercury to become excited. So that's the general process. So let's put that into words. So first of all, your electrons are emitted from a filament. Okay, so we've got that there, and the electrons then will move through your mercury tube. So that's what's going to happen next. So pressure, gas. So that's your first part of explaining this. What's going to happen next is they collide with orbital electrons in the mercury. So let's get that down. Okay, so we've got that. That's what happens. So we've got them collide with the mercury vapor, and the final stage is that they transfer their kinetic energy to increase the energy level of the orbital electrons. That's what we've got finally. The colliding electrons transfer their kinetic energy to increase the energy of the orbital electrons, or the way you can think of it is they've increased their potential energy because they've moved further away from the nucleus there. So those would be the 3 points you're looking for there. Okay, so then next part, what is the purpose of the coating on the inside surface of the fluorescent tube? So the first key thing here is to say that when the mercury electrons de-excite, they emit UV photons. So that's what we've got there, and you need to be specific that UV photons are emitted. So this is where the coating comes in. So the coating absorbs UV photons and becomes excited. That would be your second statement there. And then the coating electrons which are excited are then going to cascade down the energy levels. And in doing that, cascading down the energy levels, they're going to emit visible photons. So what does cascading down the energy levels mean? It's some terminology you see quite a lot. So the coating is going to have these energy levels, sort of like something like this. A UV photon will excite it to a very high level, and we know that the electrons can take all these different pathways back down to ground. Some of them might go all the way, some of them might take all these. And this process going down all these different paths is called cascading down the energy levels. And then if we have a look at these these lower energy ones are going to be in the visible spectrum there. So we're not going to get all visible, but we're going to get a large number of it once it cascades down the energy levels there. And that's what that means. Okay, so let's move on to the next question. So we've got the lowest energy levels shown in this, and obviously this diagram is not to scale, but never mind. So we've got the ionized state up at the top at 0 and the ground state down at minus 2.18, and that's in times 10 to the minus 18 joules. I want to calculate the frequency of a photon due to transition from 4 to 3. So essentially during this transition right here. So what we're going to do is we need to know the change in, the energy of the photon is going to be equal to the change in energy of the electron. So that's do minus 0.59, but it's going to be the modulus of that change, because any energy lost by the electron is going to be gained by the photon. So let's take the modulus of this, minus 0.26 times 10 to the minus 18, and that gives us an energy of, let's just quickly calculate that. And I've been a spanner and left out a second negative sign. 10 to the minus 18 gives us once you take the modulus, that becomes plus 0.33 times 10 to the minus 18 joules. So what we need to do is divide that by Planck's constant, so divide by 6.63 times 10 to the minus 34, and that gives us a frequency there of 4.997 times 10 to the 14, which is going to be 5.0 times 10 to the 14 hertz. Once we've got the right number of significant figures there. So that's going to be the frequency of the photon emitted there. Draw an arrow on figure 1 to show a transition to a photon of a longer wavelength than that one. So longer wavelength means lower frequency. Lower frequency means lower energy. So what we're going to want is a smaller energy transition, say from 3 to 2 there. Okay, so let's continue. Alrighty, so we've got an unstable nucleus, and it can decay by emitting a beta minus particle. What part of the atom is the same as a beta minus particle? Well, a beta minus particle is an electron. So it changes for any and A and Z when X decays. So during a beta decay, A stays the same. Because what you're going to get is a neutron turning into a proton, so you're going to have the same nucleon number, and proton number is going to increase by 1 because the neutron's turned into a proton. Okay, so in the process of beta minus, we get an antineutrino being released. So do we have any details? No, so it's just going to want a general equation here. So we're going to have a neutron going to a proton plus an electron plus an anti-electron neutrino, or you could have written this a z of x goes to a z plus 1 of y plus, again, an electron and an anti-electron neutrino. So either way would have been fine. Those are perfectly valid equations for this decay there. State and explain which conservation law may be used to show that this is an anti-neutrino rather than a neutrino that's released. So we're looking at electron lepton number being conserved. So we look before the decay, we've just got a neutron. So let's just write out the decay there so we can attach numbers to it. Plus blank. So before the decay, we've got a electron lepton number of 0. We've got a proton, got a number of 0. An electron has an electron lepton number of +1. So therefore, you must have a -1, which means you've got an anti-neutrino there. So let's go with left-hand side has a total of 0. Right-hand side must have 0. Put those two things together, and an anti-lepton is needed there. So that's the logic for answering this. So that's why you need the anti-electron neutrino, not just a neutrino. What must be done to validate the predictions of an unconfirmed scientific theory? So you've got a theory which is known as a hypothesis. So the first thing you must do is you must test your hypothesis. And if you think it's been successful, and repeat tests. So you need to be able to show you can't just do it in one set of experiments, that it can be repeated, and often it's tested by someone else, so you can show it's reproducible. And then either one of two things will happen here. It will end up being accepted, or it will end up being rejected, and most of the things will end up in this section right here, rejected, because most hypotheses turn out to be wrong. Science is all about being wrong, pretty much. It's very rare that you end up being correct, which is why there are not that many Nobel Prizes flying around. So that's the process for getting an unconfirmed theory to be validated and accepted. All right, so let's move on to the next section. Okay, so we're going to look at the photoelectric effect and how it supports the particle nature of light. In such experiments, light is directed at a metal surface. Explain what is meant by the threshold frequency. So a threshold frequency is the evidence to support the particle model, and what it is the minimum frequency at which electrons can be emitted, or the frequency below which there'll be no emitted. So let's do that. Alright, so that's what we've got there. So the frequency below which incident radiation cannot cause a photo emission. So it's the frequency of the incident radiation that's important here. So let's explain why the photoelectric effect is not observed below the threshold frequency. So first thing to say is that photon energy is directly proportional to frequency. So that's what we've got there, and we get that from the equation E equals HF. Okay, so essentially how that works is each material has a fixed work function, and if the photon energy is less than the work function, there cannot be an emission. So that's the second statement there. So that's what we've got. Below threshold frequency, the photon energy is less than the work function, so no electrons can be emitted. Okay, so then we've got a calculation based on this. So we've got light of wavelength 5.4 times 10 to the minus 7, and it's incident on a metal surface with a work function of 1.4 times 10 to the minus 19. Calculate the energy of a single photon of this light. So E equals HF equals HC over lambda. That's actually in your formula sheet as well, but we're just substituting the wave equation into there. So let's put the numbers in. So 6.63 times 10 minus 34, Planck's constant, times 3.00 times 10 to the 8, speed of light, 5.40 times 10 to the minus 7. Plug all those numbers in, and we end up with 3.68 times 10 to the minus 19 joules there. To 3 significant figures, because all the numbers we used are 3 significant figures. We want to know what the maximum kinetic energy is. So the general equation you have is the work function plus Ke max. So therefore the Ke max is going to be photon energy minus the work function, so 3.68 times 10 to the minus 19 minus 1.4 times 10 to the minus 19, 1.40 times 10 to the minus 19 joules. And if we do that correctly, we end up with 2.28 times 10 to the minus 19. That's a 19 joules. That is for the kinetic energy. Okay, so let's move on. So it wants us to then calculate maximum speed. So we're going to use your kinetic energy equation, half mv squared, where v is actually the speed. So to get the velocity, or speed, sorry, we need 2 times the kinetic energy divided by the mass square rooted. And if we do that, we end up with 7.1 times 10 to the 5 meters per second there, once we put all the values in, like the mass of the electron and our kinetic energy. Okay, so we've now got the velocity. So it wants us to work out the de Broglie wavelength. So we calculate that using Planck's constant and the mass and the velocity. So 6.63 times 10 to the minus 34. Let's plug in 9.11 times 10 to the minus 31. And then we times that by our answer, or our unrounded answer, blah, 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 times 10 to the 5. When we do that, we end up with 1.03 times 10 to the minus 9 meters. So not too far off the size of an atom, or about 10 times the size of a hydrogen atom, approximately there. Okay, so that concludes this section here. Let's move on to some electricity. Okay, so we've got a sample of conducting putty, and it's rolled into a cylinder, and we've got its length, we've got its radius, and we've got its resistivity. So you want to know what the resistance is. So resistance is resistivity times by length divided by area. That's resistivity times by length divided by pi r squared. And when we put in the values, so we've got 4.0 resistivity times 6.0 divided by pi times by 1.2. And let's take the powers of 10 separately, which is always quite useful. 10 to the minus 3 times 10 to the minus 2 times by 10 to the minus 2 squared. And we put all those values in, we end up with a value of 0.53 ohms to the 2 significant figures there, because the data we've used is 2 significant figures, and that's one of the marks of this question, will be for giving it to 2 significant figures. Okay, so let's continue on. The putty is now reshaped into a cylinder with half the radius and a length which is 4 times as great. Determine how many times greater the resistance is now. So the original equation was L over A. It's now R equals rho L, 4 times the length, over pi r squared. And we've halved the radius, so that's squared, so that's a quarter. So that means that the resistance has been times by 16 once we put the 4 and the quarter together. So it's 16 times greater than its original resistance there. Okay, let's continue. Okay, so we've got the same kind of system. So we've still got a cylinder of conducting putty. Described how you use a voltmeter, ammeter, and other equipment to determine resistivity. He wants a circuit diagram, measurements, how you'd use your measurements, and how to improve the precision of your measurements. So the basic circuit diagram is like the one you're going to see there. You've got an ammeter in series with your putty and your voltmeter in parallel with the putty here. So that's your basic system. So what we're going to do is we're going to look at keeping one part of the resistivity equation the same. So this is the general equation we're going to be dealing with. So we're going to need to keep one of length or area the same, change the other one and see its effect on resistance. That will help us get resistivity. So what I'm going to do is I'm going to keep the cross-sectional area the same. And what you can see here in slightly, frankly, untidy handwriting is we're going to keep cross-section area the same, and we're going to measure it using a micrometer, and we're going to measure it in 3 locations, and that will allow us to determine what the area is. So what the general idea behind what I'm doing is I've got a cylinder of conducting putty with consistent cross-section area, and what I'm going to do is I'm going to make connections at different lengths. So very much like the practical on resistivity. So that's what we're going to do is we're going to use a length of 5 centimeters. We're going to measure V and I, and then we're going to get the resistance for that length using V over I, and we're going to repeat to get an average resistance there. So that's one measurement, and what we're going to do is I'm going to run out of space here, repeat 6 times from L equals 10 centimeters. So I'm going to do 10, 15, 20, 25, 30 to 35 centimeters. So we get a range of lengths and a range of resistances. And what you're going to do is you're going to plot a graph of length with resistance, and it should look something like this, the gradient of which is resistivity divided by the area. So what we're going to do, final step, to get resistivity, you're going to take the gradient and you're going to times it by the area, which we've already determined, and that would give a resistivity of the measurement. So we've done a few different things to ensure precision here. So we've used a micrometer and done repeat readings of the cross section, or the diameters, to give cross section area. We've got 7 different measurements here to get an R versus L graph, and using the gradient that increases the accuracy of what we're doing as well. So there's a few different things in there that check those boxes. Okay, so let's move on from this. Okay, so we've got a circuit, we've got 4 brand new cells, each with an EMF of 1.5 and no internal resistance. So we've got 2 in parallel and we've got 2 in series. So it wants us to calculate the total resistance of the circuit. So you can see that this section here is in series with this whole section. So the total resistance is going to be the resistance of the first one plus the resistance of the second combination. So that's going to be like this, because we need to find out what the resistance of the combination is. So a quarter plus a quarter is a half. 1 over a half gives us 2. So that's going to come out as 6.0 ohms there when we calculate this. So then we're going to calculate the total EMF. So we've got 2 in parallel, which has no effect on the EMF. So 2 1.5s in parallel gives us an EMF of 1.5. 2 in series gives us 3. Add those 2 together gives us 4.5 volts there. There's not really much working you can show from that. You just need to know how to combine your EMFs. Okay, so let's move on to the next page. Okay, so then it wants to work out the current passing through cell A. So because the two cells are identical, the current's going to split in half through each of those cells. So let's first of all work out what the total current is, and then we'll split it in half. So our total EMF was 4.5, our total resistance was 6, so that's going to give us a value of 3/4, and then the current through A is going to be half of the total because they're identical resistors. So that's going to be 3/8, which is 0.375 amps there. We never leave answers as fractions in physics. Then it wants to calculate the charge passing through cell A in 5 minutes. So charge is current times time. So it's 0.375 times by 5 times by 60. And let's calculate 375 times by 5 times by 60, and we get a value of 112.5 1.1 times 10 to the 2 coulombs. So the appropriate number of significant figures there with the right unit of coulombs. Each of the cells can provide the same amount of electrical energy before going flat. State and explain which two cells in the circuit you'd expect to go flat first. The ones I expect to go flat first are C and D at the same time, because the current passing through C and D is double that of A and B. So that would be the first point I'd make. So the power delivered is IV, where the potential difference across each of them is just going to be the EMF, and energy is power times time, so we can write that EVT, or in this case, because the potential difference across each of them is their EMF, is current EMF T. So we can see that having double the current means you deliver double the energy, or as I interpret, that means they're going to last half as long. So let's put that into words. And so in terms of words, if you're delivering double the current, you're going to deliver double the energy, so you're going to last half as long as the ones that are supplying half the current, and so half the energy there. That's the logic going on here. Okay, so let's flip over. So we're going to look at some alternating current. If you're currently in year 12 on the new specification, I would ignore this question. This is now year 13 stuff, but I will go through it anyway. So we've got an alternating current source connected to a resistor in a complete circuit, and we're measuring the potential difference using an oscilloscope. And we've got Y gain of 5.0 volts per division, time base of 2.0 milliseconds per division. So the peak voltage is half the peak to peak. So peak to peak is 4 squares. So peak is 2 squares. 2 times 5 gives you 10. And that's what you can see there. And what's the RMS next, which is the peak divided by root 2, which gives you 10 over root 2, so 7.1. Again, straightforward. Time period of the signal. So if we look at the distance between maxima here, so 1, 2, 3 squares, so 3 times 2 milliseconds gives you 6 milliseconds. Again, straightforward. So last question. So the last thing we want to do is work out frequency, and you should know frequency is 1 over the time period. It's 1 over 6 times 10 to the minus 3, and when we plug those numbers into the old calculator, we end up with 167 yada yada. So let's write that as 1.7 times 10 to the 2 hertz there, to 2 significant figures, because we've got like 6.0, so 2 significant figures would be appropriate there, which concludes this paper. I hope you found that useful. If there are any queries, please do let me know. If you think my handwriting is messy, please feel free to not let me know. I already know that, which is why obviously I talk through it as I'm going through. So thank you very much for coming and watching. I hope you found that useful. The next few videos in this series looking at Unit 1 papers should be coming out soon.